would be our lab time. And I assume everybody got my email. I have posted a review. Excuse me. I posted a modified schedule in Brightspace. And all I've done is taken today's lab and subsequent labs and just shifted them down 1 week. And that will be in effect until we get to spring break. And then after spring break, everything will go back to normal. Okay. So, chapter 3. And this is, let's move it a little bit closer. There we go. Number 1. All right. Naturally occurring copper exists in 2 isotopic forms, copper 63 and copper 65. We recognize those as the mass numbers. The atomic mass of copper is 63.55 AMU, atomic mass units. What's the approximate natural abundance of copper 63? All right. To work this problem, we know that the isotope copper 63 is not going to be exactly 63 atomic mass units. But in order to work the problem, we have to assume that because we're not given the exact number. So the way we'd work the problem is we'd say, what's the relative abundance of copper 63? So it'd be 63 atomic mass units. And that would be multiplied times its relative abundance. Then I'm going to let that equal to X. Well, if there are only 2 isotopes, and the relative abundance of copper 65 should be 1 minus X. Like that. And remember, the X then would not be percent, it would be a fractional value. And then we just multiply that times 100, and that'd give you percent. And once we've accounted for the contribution of this one plus the contribution of that one, the value is 63.55 atomic mass units. So now we have an equation and one unknown. This one is obviously going to be 63x. This one's going to be 1 times 65 minus 65x. Okay? So we're gonna just solve this for x. 65 we can bring on to the other side. So this would be 63.55 minus 65 equals 63 minus 62. Okay? Excuse me, 65. So 63 minus 65 is minus 2x. So x is going to be whatever this is. 63.55 is 1.545 divided by 2, which is 0.725, and this would be equivalent to 72.5%. Okay. Now, there's no 72.5 there as a selection, so we picked the best answer. And the best answer would be, well, of course, the problem says, what's the approximate natural abundance? So the approximate is 70. That's the closest one we can get, 70%. Okay, that's how we work that problem. Okay, number 3. All right, I'm going to have to use something a little more aggressive here. There we go. All right, number 3. The average mass of a carbon atom is 12.011. And that would be in atomic mass units, because it says carbon atom. Assuming you were to pick up only one carbon unit, which would be the atom, the chances that you would randomly get one with a mass of 12.011 is what? Right. I think we went over this one in lecture. The chances of getting an atom with exactly that mass is 0%. That's because it's a weighted average. That's not the value that's assigned to any one of the carbon atoms. All right, number 4. What's the mass of 4 atoms of copper in grams? This is the dimensional analysis problem. 4 atoms of copper. What we want is grams. That's where we're headed. So how do we get there? Well, we don't have any conversion factor that goes directly from atoms to grams, but we do have one that goes from moles to grams. So we want this one to be, convert this to moles first. Right, Avogadro's number. Okay, that gets rid of atoms. Now we can convert moles to grams. And notice our target is in the numerator. Target's in the numerator. That's a dead giveaway. How do we know what is the average mass of copper? Well, we just looked at it a minute ago. It was right up here. It was 63.55. Or you can look it up in the periodic table. And I got one I'm hanging on my wall here. Let's see. Yep, that is correct. 63.55 grams per mole. Remember, that value is either atomic mass units per atom or grams per mole. Okay? So then we just say 63.55 times 4 divided by Avogadro's number, and we should get 4.22 times 10 to the minus 22. All right. That's number 4. Now, I've just picked out some that are representative, right? There are a lot more problems in here than we're going to work today. All right, I think that's getting a little weak. Let's try this one. Number 6. That's better. Okay, number 6 says you have a sample of zinc and a sample of aluminum. And you have an equal number of atoms in each sample. Which of the following statements concerning the masses is true? All right, so if we have equal number of atoms of zinc. So say we have n number of zinc atoms and n number of aluminum atoms. What can we say about the masses? Well, If we have exactly the same number, then we know from Avogadro's law that they're going to have different masses. As long as they have the same number of atoms, they will have different masses, and they will have different masses because the individual atoms are different masses. Now, zinc, let's see, let me look at my periodic table here. Zinc is 6538. Atomic mass units, and aluminum is 2698. And that's per atom. Okay. So if we have the same number of atoms, then, and we multiply them by the number of atoms, which one's going to weigh more? Zinc is going to be heavier than aluminum. Now, let's see if we can find one of these answers that fits that scenario. The mass of zinc sample is more than twice as great as the mass of aluminum. Okay? This would be about 27. So 27 times 2 is 54. Yeah, zinc would be twice as much. Now, we can look at the others, but we found the right answer, and there are no odd ones in here, like none of the above, two of the above, so forth. So once you find the right answer, you can stop and go to the next one. So A is the correct answer. The mass of zinc is going to be more than twice that of aluminum. All right, number 7. A sample of ammonia has a mass of 43.5 grams. 40, wait a minute, 43.5 grams of ammonia. Now, fortunately, we don't have to know what the formula of ammonia is. I can give it to you anyway. That's ammonia. How many molecules are in this sample? Oh, we do need to know. Why? Because molecules is counting and grams is mass. We need a connection between the two. And if you don't know what the molar mass of ammonia is, you can't make the connection. So you do need that value. And if you don't remember what the formula for ammonia is, then all you have to do is ask me during an exam and I'll tell you. Okay, so what's the molar mass of ammonia? Well, nitrogen is 14.01, and 3 times 1.01 for hydrogen. So that's 407 there, grams per mole, like that. So now we have a dimensional analysis problem. We want to find out how many molecules. So the first step is to find out how many moles. Grams on the bottom, moles on the top. 17.04 cancels the grams. Now we can change the moles and molecules. And what's the magic number? Avogadro. Okay. So now we cancel moles and we ended up with molecules. And if we do our math correctly, the answer should be 1.54 times 10 to the 24th molecules. Okay. That's D. All right, number 8. How many moles of hydrogen sulfide are contained in a 49.7 gram sample of this gas? In this case, you need to know how to go from hydrogen sulfide to the formula. You know it's got hydrogen, you know it's got sulfur, and you know that normally hydrogen is a +1, sulfur would be -2. It's the same as oxygen, it's in the same family. So that means we have 2 hydrogens. All right, 49.7 gram sample. Okay, and we want to find out how many moles. Well, in this case, all we need is the molar mass. And one conversion factor is all that's required. Grams on the bottom, moles on the top. So 2 hydrogens is 2.02, and sulfur, you have to look that up, right? It's not given here. So you have to look it up in the periodic table, and that's 3207. So that's 9043. 34.09. Grams cancel. And we really don't even need a calculator if you look at the answers, right? This one is smaller than that one, so we know the answer is going to be greater than 1. That means A can't be it. We know it's not going to be it's not going to be as big as 83.8, and it's not going to be twice, right? Twice that would be 78, right? So it's not going to be E, it's not going to be C, and definitely not going to be D. So by process of elimination, we know it's going to be B, 1.46. Or you can use your calculator, whichever you prefer. All right. Let's see. Yeah, still coming down out there. Number 10. For which compound does 0.256 mole weigh 12.8 grams? All right. So here we need to compare the molar masses of each of those compounds to the calculated molar mass from the data that we're given. Grams per mole, which means 12.8 grams and 0.256 mole. So our target molar mass is 12.8 and divided by 0.256, which is 50. Grams per mole. Okay, we can set up assembly line. So for C2H4O, C2H4O, CO2, CH3Cl, and C2H6. So for the first one, carbon, you look up carbon, is 12.01. So we got 12.01 times 2. That's 24. Plus 4.04 for the hydrogens, and plus 16 for the oxygen. And that's 44.06 grams per mole, right? So that's not it. Carbon dioxide is 12 plus 32. 2 times 16 is 32. And 12.01 is 4401. That's not it. Okay, now we got 12.01 here, and 3.03 for the hydrogens, and 35.45 for the chlorine. and that's 49.49. That's a good candidate, right? That's probably the answer. Let's check the last one to be sure. 12.01 times 2, and then 6.06 for the hydrogens. Yep, that's 3008. So this one is the closest one, right? Now, technically, it's not exactly 50, right? So probably we should have worded it for which compound does 0.256 mole weigh 12.8. Actually, which one comes closest would be a better way to word that problem. So technically, since this is not exactly the same, you could say E. E would be a valid answer. And you could argue your point, right? All you have to do is show me your calculations and you'd get it right. All right, number 11. Calculate the molar mass of barium sulfite. Okay, you have to know how to write this compound. What kind of compound is it? Is it a type 1, type 2, or type 3? Well, barium's a metal. Sulfite is a polyatomic ion, so it's either a type 1 or a type 2. We look at barium. Barium is an alkaline earth. It always has a 2+ charge. That's a type 1. So we have barium and sulfite. You can look it up in the useful information, CO3. And that's 2-. Barium is a 2+. We only need one of each. So there's your formula. And calculate the molar mass. Barium, I need to get something closer at hand so I don't have to strain my neck to read that. Periodic table. I just have to find one. It's not there. Oh, crap. I guess I'll have to get closer to see it. 137.33. 137.33. And sulfur is 3207. And these are all grams per mole. And then 3 times 16. We add those together. 2.7, and 3 times 16 is 48. 217.40. 217.40 grams per mole. So that would be E. E would be the correct answer. What's the mass of 6.761 mole sample of sodium hydroxide? All right, that's number 13. Here we go again. You have to know how to write the compound. Right? Sodium, always a +1. Hydroxide, polyatomic ion with a -1 charge. That's the formula. So if we know that, then we look up sodium, which is 23, 2 decimal places, 16 for oxygen, and 1.01 for hydrogen. 40 grams per mole. Now that we've got 6.761 mole sample, we want to convert that to mass. Dimensional analysis says moles on the bottom, grams on the top. So we have 40.01. Moles cancel, and it's 6.761 times 40.01, which is 270, 4 places, 0.5 grams. The closest answer we've got there is 270.4, so B is your answer. When in doubt on a multiple choice, pick the best answer. Oh, they're giving you ammonia on that question. All right, 15. One molecule of a compound weighs 2.93 times 10 minus 22 grams. 2.93 times 10 to the minus 22, was it? Yes, grams. And this is per molecule. Okay. The molar mass of this compound is, instead of grams per molecule, we want grams per mole. And we're only going to convert that unit. We've already got grams. We want to convert molecules. So we want molecules in the numerator and moles down here. So this is 6.022 times 10 to the 23rd molecules. And if we do our math right, we should end up with 176 grams per mole. Okay. All right. 17. Put it on screen here. 17. All right. A compound. Let's see. Let me check my list here. See if we got anybody new. Okay, we're good. A compound is composed of element X and hydrogen. Probably like that. Although some compounds would have the hydrogen first. We don't know that yet. Let's see, we've got more information. Analysis shows the compound to be 80% X by mass. 80% mass X. Okay? With 3 times as many hydrogen atoms as X atoms per molecule. So now we got 3 like that. Which element is element X? All right. What we need to determine X is, what can we get from this information? We're still talking about mass. And mass is not numbers of protons. If we knew the number of protons, it'd be simple. We just look up the atomic number, we'd find our element. But the second best thing is to know the molar mass of the element. If we can determine the molar mass of the element, then we can get pretty close. Usually you can find the element exactly. So what do we need to know X? We need to know grams per mole for X. Well, let's see. If we have 3 times as many hydrogens as X, we do know the molar mass of X. I mean of hydrogen, right? So if we just assume that we've got 100 grams of compound, say we assume 100 grams. compound. How much of that is X? Well, that makes 80 grams of X and 20 grams of hydrogen. Okay? So 20 grams of hydrogen would be how many moles? Let's see. Hydrogen is 1.01 grams per mole. So we divide 20 by 1.01. And that's 19.8. 19.8 moles of hydrogen. Okay. If we got 19.8 moles of hydrogen, how many moles of X do we have? We actually have a third, because this equals 3 times X moles. So X would be 1/3 of that. 19.8 divided by 3 is 6.6 moles of X. Well, now we know the mass. We know the mass of X, and we know the moles of X. So we just say 80 grams divided by 6.6 equals, and that should be our molar mass for X. 12.1. All right, what's the closest one to that on the periodic table? You just follow along, top to bottom, left to right, until you get to something that's close to 12.1. The closest we have is 12.01, which is carbon. So our best guess is that this is carbon. All right. Number 18. Which compound contains the highest percent by mass of hydrogen? All right. We're going to need our assembly line. Oops. That dropped. Okay. Put that down there. So we've got these 5 compounds: HCl, H2O, H2SO4, H2S, and HF. And for those, we want to know what's the highest percent by mass of hydrogen. Okay, so remember how to calculate the percent by mass? You need the molar mass of the compound, then you need the molar mass of hydrogen in the compound. Actually, the molar mass times the number of moles of hydrogen in the compound. So the first one would be percent mass. We would want 1.01 divided by 1.01 plus 35/45 times 100. Water would be 2 hydrogens, 2.02 over 2.02 plus 16 for oxygen times 100. This would also be 2.02 for hydrogens plus sulfur, which is 3207, plus 4 oxygens. 4 times 16 is 64 times 100. And then this one is 2.02 per, and sulfur is 3207. But we also have to add the hydrogen in there because this is the total mass. And then HF is 1.01 for one hydrogen, and then 1.01 plus 19 for the fluorine. Okay. Then we simply do the calculations. Let's see, 1.01 and 35.45 plus divide is 27.7% hydrogen. 2.02, 16 plus, and then divide, and that's 11.2% hydrogen. Let's see if I did that right. 1802, 2.02, enter 18.02, 100. Yes, that's right. Then 2.02 and 32.07 is in the denominator, and then divide that, and I get 5.9. All right. 2.02 again. Oh, excuse me. That's this one. I left out 64. So 32.07 plus and 64 plus, and then divide. That's 2.1. Okay, and then the last one, 1.01 and 19 plus divide is 5.05. 5.05%. It looks like I made a mistake. Let's try that again. 1.01, enter, and 35.45, divide. I did make a mistake. This is 2.8%. Let's check that one again. 2.02, enter 16 plus. So 18.02 down here, divided into 2.02 is 11.2. Oh, there we go. Water has the highest percent by mass of hydrogen. Okay. $19. And we're still in chapter 3. A substance contains 35 grams of nitrogen, 5.05 grams of hydrogen, 60 grams of oxygen. How many grams of hydrogen are there in a 153 gram sample of this substance? So here we want to know what's the percent composition of hydrogen. Then we can use that to determine the mass of hydrogen in the 153 gram sample. So if we have hydrogen 5.05 grams, and then it's also in the denominator, then the other components are nitrogen and oxygen. Yeah. Now, there are two ways to work this. If we want to express it in percent, we have to multiply by 100. But if we want to know just the fraction of hydrogen by mass, then we can stop here. And that will allow us to multiply that fraction times 153 and give us the value without having to go through a percent conversion. So if I just do this calculation, 60, I get 0.505. 0.505, and this is hydrogen mass. And that's simply the fraction of hydrogen in that sample. So 153 grams times 0.505 is 7.72 grams of hydrogen in that sample. See? And we skip the part where we have to convert percent, because percent is, actually it would work either way. If we converted that into percent, it would be 50.5%. 50.5 parts, grams of hydrogen per 100 grams of sample. That's what 50.5% means, parts per 100. Then we could just say 153 gram sample. And we'd end up with exactly the same value. Either way works. 22. Each molecule of testosterone contains 19 atoms of carbon plus other atoms. The mass percent of carbon in testosterone is 79.12%. What's the molar mass of testosterone? This is a dimensional analysis problem. And in order to determine the molar mass, we need both the mass and the moles. All right? So what information do we know? 19 atoms of carbon are in testosterone. 19 atoms of carbon per molecule. Right? Okay. We also know that the mass percent of carbon is 79.12%. 79.12 grams of carbon per 100 grams of the molecule. Yeah. 19 atoms per molecule. And we've got 12.01 atomic mass units per atom. That's atomic mass units per molecule. Right? Yeah. That's 12.01 is 22.82 atomic mass units per molecule. We know that atomic mass units per molecule translates, it's like atomic mass units per atom would be, atomic mass unit would be grams per mole. So this is also equal to 22.82 grams of carbon per mole of testosterone. Now, once we got this part, we can convert grams of carbon to grams of molecules. Grams of carbon, grams of testosterone. Okay, and that's 79.12 per 100. All right, so that's 288 grams per mole. Closest one to that is E. I was making that a whole lot harder than it needed to be. It was really, really a simple conversion. I think I need a fresh marker. These markers are getting weak. Dude, what time is it? Past 1:30. Okay, it's coming up on 1:45, right? 1:45. So that means we're getting ready to go into lab time. Yeah. So we can finish our review today. It's probably fortunate that we're not going to have a lab today because I need the time to finish the review. All right. We did that one. 24. Iron oxide, an oxide of iron has the formula Fe3O4. All right. What mass percent of iron does it contain? All right, we know how to calculate this one. We just need the molar mass of the compound and how much iron does that represent? So iron is 5585. So 3 times 5585 in the numerator and 3 times 5585 in the denominator, plus 4 times 16 times 100. That's how you set the problem up, and we should end up with 72%. Now, an interesting fact is if we were to try to calculate the charge on the iron, because this is definitely an ionic compound, iron and oxygen. Well, oxygen is going to be 2 minus, so that's 8 minus, correct? So we need 8 plus for those irons, and each one of those irons is going to be 8 divided by 3. That's not an even charge, right? So, but this is the correct formula for an iron compound. So what we've been able to determine over time is that this is actually a combination of this one and this one. Okay. So there's 2 plus 1 is 3, and 3 plus 1 is 4. It's a mixture. It's actually it's a crystal lattice with these two different ratios embedded in it, in case you're interested. Number 26. Ammonium chromate. Isn't that nice? We're actually given the formula. Contains what percentage nitrogen by mass? All right. The trick to this one is to recognize that you've got two ammoniums in this compound. So you need 2 times 14.01 in the numerator. And you need 8 for the hydrogens, and you also still need the nitrogens in here. Then you need chromium. 1 chromium, which I have to look it up. 52. And then 4 times 16 times 100. And that should equal 18.4% nitrogen. Okay? That's how you work that one. One of the easier ones. Okay. Number 30. A hydrogen is found to be, I got to move that, 85.6% carbon by mass. A hydrocarbon, excuse me, a hydrocarbon. And in parentheses, we say, what is a hydrocarbon? It has carbon and hydrogen only. So if it's 85.6% carbon, what percent is hydrogen? Well, it's just 100 minus that, right? So that'd be 4. This would be 4, and this would be 1. Let's see if that adds up. Yeah, okay. What we want to know is the empirical formula. Remember, we can't convert percent to moles. And we have to convert to moles in order to get the proper ratio of atoms to atoms. So we have to assume that we have a 100-gram sample. And out of that is 85.6 grams of carbon, 14.4 grams of hydrogen. Now we can convert. This is 1.01 gram per mole. And this is 12.01 grams per mole. So now we can establish the mole ratio or the atom ratio in that compound. 85.6, 12.01 is 7.13. And then 14.4 and 1.01 is 14.3. Okay. So we need whole numbers. That's not whole numbers yet. So what we do is divide through. Okay. This is equal to 1. And this is about 2. Okay. So that means our empirical formula should be 1 carbon and 2 hydrogens, or B. That's the closest one we have in that group of answers. All right. Number 32. All right, the empirical formula of styrene is CH. So this is the empirical formula. And the question is, what's the molecular formula? Remember, in order to find the molecular formula, we need a multiplier to multiply through by the subscripts. Now, the simplest way to do that is to ratio molar masses. The empirical mass would be 12.01 and 1.01 grams per mole. This is what I call the empirical weight or the empirical mass. We're actually given 104.1 grams per mole of the molar mass. So if we ratio those two, then we should get our value for X. And it's about 8. So our formula should be C8H8. Excuse me, is B. Come on. One of my cats once in the room, so you better let him in. All right. 33. All right. This one, adipic acid contains these percentages of carbon, oxygen, hydrogen. What's the empirical formula? We work this exactly the same way as that previous problem with carbon and hydrogen. It's just now we have 3 elements. In the interest of time, I'm going to let you work this one out for yourself. We're given percentages. You just say, you assume a 100-gram sample, which means now you have 49 grams of carbon, 43.8 grams of oxygen, 6.85 grams of hydrogen. Convert those to moles, then ratio them so that you get whole numbers. That will give you your empirical formula. And you should come out with C3H5O2. All right, let's see. This is vitamin C. All right, it's another just such problem. Maybe we'll do 34 completely, because problem 34 works through the empirical formula all the way through to the molecular formula. And this will give you some continuity in the process. So we'll do 34. Okay. Our compound has carbon, hydrogen, and oxygen. We know that it's 40.9% carbon. By mass, 4.58% hydrogen. And oxygen would be what? Well, if it's only got carbon, hydrogen, and oxygen in it, then we just need the difference. 40.9 and 4.58 subtracted from 100 is 54.5. 54.5%. All right. Now we know that we've got 40.9 grams, 4.58 grams, and 54.5 grams. And we can convert each one of these to the number of moles. This mass ratio is fixed according to the law of definite proportions. If the mass is fixed, then the number of moles is fixed for each one. We just have to determine what that is. Carbon is going to be 12.01 grams per mole, 1.01 grams for hydrogen, and oxygen is 16 grams per mole. Go. So 40.9 divided by 12.01 is 3.405. 3.405 moles of carbon. 4.58 divided by 1.01 is 4.535. 4.535 moles. And 54.5 divided by 16 is 3.406. 3.406 moles. Okay. Now we need to find the ratio that's nearest a whole number. If we divide this one through by 3.405, and this one by 3.405, and this one by 3.405, this one's going to be 1, this one's going to be really close to 1, and this one's going to be 1.33. Okay? So now we've got 1 1/3 here. How do you get rid of a third? You multiply by 3. So if we multiply times 3, then we get 3, 4, 3. And the empirical formula then would be C3H4O3. All right, now we got to go to molecular formula. What is the empirical weight of this? What is the empirical weight of that formula? Well, 12.01 times 3 and 4.04 for the hydrogens, and then 48 for the oxygens. 3 times 16 is 48. This is, the empirical weight is 88.07. And 180 is the molecular weight. 80 point, that's it. Grams per mole. What's the ratio of those two? 180. That didn't work out. 88.07 enter 180. There we go, 2. The ratio is about 2. So X equals 2, and we have C6H8O6. All right, that's the molecular formula for vitamin C, also known as ascorbic acid. All right. Number 36. How many of the following are true concerning balanced chemical equations? All right, so we got Roman numeral 1, 2, 3, 4, and 5. Roman numeral 1, the number of molecules is conserved. Is that true? No. The number of atoms of each element is conserved. on either side of a chemical reaction, a balanced chemical reaction. So this one's false. 2, the coefficients for the reactants tell you how much of each reactant you are given. When we say how much, the author of the question is referring to mass, and that's not true. The coefficients refer to how many molecules, how many moles of each of the reactants and products. Atoms are neither created nor destroyed. That is true. Number 4, the coefficients indicate the mass ratios. No, we already discounted that one. And the sum of the coefficients on the reactant side equals the sum on the product side. No. If that's true, if that ever happens, it's purely coincidental. So there's only one true statement in that list, and that's Roman numeral 3. All right, let's see here. Number 37. In balancing an equation, we change the blank to make the number of atoms of each side of the equation balance. The coefficients, right? We just covered that. What is that? The coefficients, B. That's true. Number 39. Let's see. Are we ever going to get to chapter 4? Let me go down and see. There it is. Okay. Let's go back to 37, is it? We did that one. Okay. 37 is done. 39. What is the coefficient for oxygen when the following equation is balanced? Okay. If you're new to balancing equations, use the budget method. So we would have ammonia plus oxygen yields nitrogen dioxide plus water. Okay. So our budget method says we have nitrogen, hydrogen, and oxygen in this one. 1 nitrogen, 3 hydrogens, 2 oxygens. And on this side, we have 1 nitrogen, we have 2 hydrogens, and 3 oxygens. So we don't want to do oxygen first. And nitrogens are already balanced. So we have to go to hydrogens. We have 3 hydrogens here and 2 hydrogens there. How do we reconcile that? Well, the trick that I gave you, the hint, is you cross multiply. So you take that 2 and put it over here. You take this 3 and put it over here. Now that works only when the element occurs in one place on either side. Okay, now in this case, we have 2 nitrogens, 6 hydrogens, and over here we have 6 hydrogens and 3, 4, 5 oxygens. Okay, we got to balance the nitrogens. There we go. 4 and 3 is 7. Now we put a 7 halves here. And when we get rid of the fractions, we have 7, the coefficient of 7 in front of the oxygen. That's why C is the answer. Okay, number 40. What's the sum of the coefficients of the following equation when it's balanced? All right. So we've got sodium amide. That's what that is, amide, sodium amide. And sodium nitrate. And then 3 on the other side. Sodium azide. Sodium azide is a compound that used to be put into airbags. All you'd have to do is shock it, and it would instantly produce a massive amount of nitrogen gas. And then sodium hydroxide, and then the last one is ammonia. Okay. So if we got, let's see, sodium, nitrogen, hydrogen, oxygen. Sodium, nitrogen, hydrogen, oxygen. There we go. Okay, sodium on this side, we got 2. And nitrogen, we've got 1, 2. Hydrogen, we've got 2. And oxygen, we have 3. Now let me check myself. 1, 2, 3, 4, 5, 6, 7, 8, 9. 3, 4, 5, 6, 7, 8, 9. Now on this side, we have 1 nitrogen. Excuse me. 2 sodiums. There we go. Nitrogen, 3, 4. Hydrogens, 3, 4. And oxygens, 1. Okay, here's the problem with this one. You've got elements, multiple places for the elements on either side. So you got sodium here, you got nitrogen there, you got sodium here, you got nitrogen there and there, and hydrogen split here and here. All right, so this is going to present a problem. It might even be a problem for me. Where do we start? If we balance oxygens, I think I did that before. If we want 3 oxygens, we put a 3 here. That'll give us 3 oxygens, definitely. It'll also change the sodiums to 4. And the hydrogens to 6. Like that. Okay, now if we want to balance we want to balance the sodiums. If we put a 3 here, that'll give us 4 sodiums. That'll also give us 3, 4 nitrogens. And that'll also give us 6 hydrogens. And we're balanced. That, I'll admit, that was a difficult one, because it's easy to make that thing more complicated than it needs to be. All right, that looks like a good extra credit problem there. Oh, the sum of the coefficients, excuse me. The sum of the coefficients. 3 plus 1 is 4, 5, 6, 7, 8, 9. So the sum of the coefficients is 9. Now this is a combustion of C6 is hexane, C6H14. When you combust a hydrocarbon like this, you nearly always need the fraction trick. And the sum of the coefficients for this one. I know I can do this one really quick, so it won't be a problem. C6H14, C6H14 plus oxygen always yields, is it carbon? Yeah, we put carbon dioxide first, plus water. Okay, so we have carbon, hydrogen, oxygen. We have 6 carbons, 14 hydrogens, 2 oxygens. We have 1 carbon, 2 hydrogens, and 3 oxygens. We're going to hold the oxygen till last. I'm going to balance the carbons first. So that's 12, 13, let's see, 12, yeah, 13 oxygens. And let's see, hydrogens, 14 hydrogens. So we put a 7 here, and that makes 14 hydrogens. It also makes 7 plus 12 is 19 oxygens. Now we have 19 halves here, and that balances that. Now whole numbers would be, multiply the whole thing through by 2. You have a 2 here, you have 19 there, you have 12 here, and you have a 14 there. Okay, so if we add them all together, that one's, let's see, 12, 14, 19, and 2 is 11, 15, 16, 17, 47. That would be B. So that we had to use a fraction trick. And the only hydrocarbon combustion that doesn't need the fraction trick is methane, CH4. All the rest of them, you have to use the fraction trick. Okay, 44. How are we doing on time? Okay. A reaction occurs between sodium carbonate and hydrochloric acid. Sodium carbonate. So you have to know how to write that. Carbonate is a 2 minus. Sodium is a 1 plus. So that's sodium carbonate. And hydrochloric acid, which would be an aqueous solution, but for the purposes of balancing our equation, we don't have to put the state. But it will produce sodium chloride, carbon dioxide, and water. Sodium chloride, carbon dioxide, and water. Okay, so if we have sodium, carbon, oxygen, hydrogen, and chlorine, then we have 2 sodiums, we have 1 carbon, we have 3 oxygens, we have 1 hydrogen, and 1 chlorine. On this side, we have 1 sodium, 1 carbon, 3 oxygens, and we have 2 hydrogens and 1 chlorine. Okay, I'm inclined to go ahead with the sodium. Just say we want 2 sodiums. That gives us 2 chlorines. And if I come over here to give me 2 chlorines, it also gives me 2 hydrogens. And we're balanced. You can see it instantly that you're balanced. We need a 2 here and a 2 here. So the correct set of coefficients is 1, 2, 2, 1, 1. That's D. Okay. Number 45. I think I put this one in here so that we could use some symbolic language. A chemical reaction has the equation 2A plus B yields C. 2A plus B yields C. And the coefficients tell us the mole ratios. We start off with 2 A's and 1 B, and we end up with 1 C. So which one of these following figures best illustrates a stoichiometric ratio of A and B? So the stoichiometric ratio means what are we starting with? And we should not have any C's in our figure, right? So Roman numeral 4 can't be it because you've got C's in there. We're starting off with 2 A's and 1 B ratio. How about 1? 2 A's. 1, 2, 3, 4, 5, 6, 7, 8. 8 A's and 4 B's. That's a stoichiometric ratio, correct? So Roman numeral 1, definitely. How about the second one? 1, 2, 3, 4, 5, 6, 7, 8 A's and 8 B's. No, that's 1 to 1. And 3 is 4 A's and 8 B's, right? That's the wrong direction. The only one that's good is Roman numeral 1. That's A. 46. All right, 7.11 gram sample of potassium chlorate was decomposed according to the following equation. 2 potassium chlorates yields 2 potassium chlorides plus 3 oxygens. How many moles of oxygen are formed? All right, this is a stoichiometric problem. KClO3 yields 2 KCl plus 3 O2. 2, 2. Yep. We have 7.11 grams of potassium chlorate. The question is, how many moles of oxygen do we produce? Right? Remember, we can't go anywhere in this equation unless we have moles. So this has to be converted to moles. We need the molar mass of potassium chlorate. Potassium is 39.1. 39.10. Chlorine is 35.45. And 3 oxygens is 48. Right? 5, 5, 13, 2, carry the 2. 2, 6, 7, 8, 9, 10, 11, 12. 122.55. I think that's right. I better check. Yeah, that's right. Divide that into 7.11 is 5.88 times 10. Oops, sorry. 5.80 times 10 to the minus 2 moles. The ratio here is moles of KClO3 This is in the numerator, that's in the denominator. And the ratio is 3 of these for every 2 of those. So if I do the calculation, we should get 8.70 times 10 to the minus 2 moles. Oh, standard notation. So 2 to the left. 1, 2. 0.087. 0.087 is D. D is your answer. 47. How many grams of calcium nitrate can be produced by reacting excess HNO3, which I assume is nitric acid, with 6.33 grams of calcium hydroxide? So we're going to say calcium hydroxide, okay, reacted with nitric acid. One of the products is calcium nitrate. And what's the other product? Remember, when you react an acid with a base, you always get a salt, the combination of this cation and that anion, and then water. If you don't put that water in, you can't balance the equation. All right, I should be able to balance this without too much trouble. 1 calcium, 2 nitrates. So that's 2 hydrogens and 2 hydroxyls makes 2 waters. That's balanced. 6.33 grams of this product, 3 grams, is how many moles? So we need to convert that. We need the molar mass of calcium hydroxide. Calcium, I think, is 40.08. 2 oxygens and 2 hydrogens. $44.1. Divided into 6.33 is 0.1435 moles of calcium hydroxide. Okay, and the question was calcium nitrate. How many moles of calcium nitrate? Well, it's 1 to 1, right? So that's also calcium nitrate. 1435, right? Oops. What did I do wrong? 6.33 grams. Oh, how many grams? I'm sorry. This is the right number of moles. We now need to convert to grams. So we need a new molar mass. I should have done this. I should have done that. There we go. That would keep me honest. So calcium is still 40.08. 2 nitrogens is 28.02. And 6 oxygens, 6 times 16. So we have 40.08. We have 28.02. And 6 times 16 gives us 164.1. 64.1 times that value, 23.6. There we go. Now, why does it say 14? Oh, that's wrong. That's wrong. This is correct. 161.4. I calculated this value. Let me recalculate that value. There we go. This is 8.54 times 10 to the minus 2. Now we can multiply that times 164.1. That's 14. 14.0. B is correct. Okay. Must be the weather. All right. Lots of repetition. For this reaction, what mass of P4O10 must be consumed if 3.71 times 10 to the 23rd molecules of water are also consumed? All right. Seems difficult, but it's really not. You just need the methodical. The balanced equation is already there. P4O10 plus 6 water yields 4 phosphoric acid. Okay, we're given 3.71 times 10 to the 23rd molecules of water. We need moles. 6.022 times 10 to the 23rd molecules per mole. That'll give us the number of moles of water. Then we can move. That's 0.616 moles of water. Now we want to convert that to P4. Yeah, we want to convert it to this. The ratio is water to P4O10 is 1 here and 6 there. So we divide by 6 and we get 0.1027 moles of P4O10. So in order to do the mass, we need the molar mass of P4O10. So phosphorus is 30.97. That's times 4. And then 10 times 16. So 160 plus 30.97 enter 4 times plus. This is 283.88 grams per mole. So now we can multiply this, and we need moles on the bottom. 283.88 grams per mole, so that the moles cancel. And I get 29.1 grams, which is B. Okay. E8. How we doing? Getting low on time? 5.95 grams sample of silver nitrate is reacted with barium chloride according to this equation to give 3.17 grams of silver chloride. What's the percent yield? All right, this is easier than it looks. You remember what percent yield definition is? Equals the actual divided by the theoretical times 100. So the actual amount of silver chloride we got out of this reaction, oh, no, we don't have all the information we need. We have so many grams of silver nitrate, but we don't have the number of grams of silver chloride. Barium chloride must be in excess. So if we convert 5.95 grams of silver nitrate to moles of silver nitrate, then we can calculate the moles of silver chloride and the mass of silver chloride expected. Okay, so I'm getting ahead of myself. What we need to do is take 5.95 grams of silver nitrate and convert it to moles. So silver nitrate would be, let's see, silver is 107.87. Nitrogen is 14.01. And 3 oxygens is 48. $169.88. Okay, divide that into 5.95, and we get 3.50 times 10 to the minus 2 moles of silver nitrate. What's the ratio? 2 moles of silver nitrate yields 2 moles of silver chloride. So it's exactly the same amount. 3.50 times 10 to the minus 2 moles of silver chloride. Now we need to convert that back to grams of silver chloride, right? Yeah. Okay, so that would be silver is 107.87, and chlorine is 35.45. So that's 143.32. And that's 5.02. That's the theoretical. Oh, excuse me. Wrong place. 5.02 is theoretical. We actually got 3.17 times 100. And that's 63.2% yield. Closest one to that is D. All right. We're coming up on 2:45. And well, 3:30. I've only got 45 minutes left. Okay, let me put this over here. 59. We'll come back to 59 if there's time. Oh, wait a minute. Maybe we better do 59 because that's a limiting reactant. Yeah, we better do 59. We haven't done a limiting reactant yet. So let's do that one. Okay, we have this balanced equation, methane plus chlorine yields carbon tetrachloride plus 4 hydrogen chloride gas. Okay. What mass of carbon tetrachloride is formed? Mass of carbon tetrachloride, if 1.2 moles of methane is reacted with 1.11 moles of chlorine. Okay. Remember, whenever you have absolute amounts of reactants, one of them is going to be limiting. So if we say, normally what we would do is say, how much carbon tetrachloride would this make? And how much carbon tetrachloride would that make? And we take the least amount of each one. That's the surefire way to do it, which is probably what we should do now. So this is 1-to-1 ratio. So this one yields, let's see, let's do this. This one yields 1.2 moles of carbon tetrachloride. This one yields 1/4 of that, right? 4 of these to make one of those. So 1/4 of 1.11 is 0.278 mole. This is the limiting reactant right here. We know that only 0.278 moles of carbon tetrachloride will be made. So now we need to convert using the molar mass of carbon tetrachloride. That's 12.01 and 4 times 3545. 153.9 times 0.278 is 42.8. 42.8 grams. Okay? Or 42.7. That's close enough. That was our limiting reactant. Problem. Looks like we got another one coming up here, but it's kind of a what if, a theoretical thing. So which of the following statements is always true concerning a reaction represented by the following balanced chemical equation? All right. 2 ethanes plus 7 oxygens yields 6 waters and 4 carbon dioxides. All right, the way to solve this one, since we've got A says a ratio of masses and no limiting reactants, so we need to find out which is the limiting reactant. Yeah, what ratio of mass of ethane to oxygen would be a stoichiometric mixture. And then we already have the molar stoichiometric mixture of 2 to 7. So we need the stoichiometric mass mixture. Yep. So let's put this equation up here. Actually, we only need the first part of the equation. We have 2 C2H6 plus 7 O2. Right. We're talking about yeah, we're only talking about the reactants here, so we don't need the products to discuss. All right, what would be a stoichiometric mixture? Well, 2 moles of ethane and 7 moles of oxygen. But what would that be represented in terms of mass? Well, the molar mass of C2H6, so many grams per mole, is 12.01 times 2 plus 6.06. So this would be 30.08 grams per mole, but it's times 2. So 60.16 grams of ethane, and then oxygen would be 32 grams per mole times 7. Would be 224. So there's your stoichiometric ratio in mass. This is in moles, this is in mass. So now let's look at our questions. If we have equal masses of C2H6 and O2, there's no limiting reactant. That's not true. Equal masses, if we say we had 224 grams here and 224 grams here, oxygen would be limiting because we only need 60 grams of the ethane, right? So A is false. What does B say? If we have an equal number of moles of C2H6 and O2, there's no limiting reactant. That's false too, because an equal number of moles, if say we have 2 moles here and 2 there, oxygen would be limiting. There wouldn't be enough of them. So B is false. How about C? If we have more mass of C2H6 than O2, then O2 must be limiting. If we have more mass of C2H6, that's not worded right. Where's the mute key? The other way. The other way. It doesn't have one. There it is. Okay. C says if we have more mass of C2H6, then O2 must be limiting. All right, that's poorly worded. If we have more mass of C2H6 than what? If we have more mass of C2H6 than O2, then yes, O2 will be limiting, right? Because if we have more of this than we have that, then this is still limiting because it takes 224 grams for every 60 of this. If we have 224 here, we don't have enough oxygen. So C would be true if we interpret it correctly. D says if we have more mass of O2, then C2H6 must be limiting. That's false. I think this is poorly worded. None of these statements is true. That's false because we found one. E is false. C is the best answer, as long as we correct their grammar. What's wrong with chemists? Their grammar's kind of bad. Okay, 62. Equal masses in grams of hydrogen gas and oxygen gas are reacted to form water. Which substance is limiting? All right, equal masses. So if we're reacting hydrogen diatomic and oxygen diatomic yields water, then we need 2 here to give us 2 oxygens and then 2 here to give us 4 there. All right, this is the ratio. For hydrogen, molar mass of hydrogen gas is 2.02 because there are 2 hydrogens. But 2 times that is 4.04 grams. And this is 2 times 30, 2 times 16 is 32. Right? So there's the mass stoichiometric ratio. equal masses. If we have equal masses, say we have 32 grams here and 32 there, then oxygen is limiting. Okay? So A is the correct answer. Hydrogen gas is not limiting. Water's a product. It can't be limiting. Nothing is limiting means stoichiometric, and that's not true. So A is the only one that can answer that question. Let's see, we're going to do 64. For this reaction, nitrogen plus hydrogen yields N2H4, which is hydrazine. If the percent yield for this reaction is 82, what's the actual mass of hydrazine produced when 25.57 grams of nitrogen reacts with 4.45 grams of hydrogen? This is a multi-step problem. You're given grams of reactants, so one of them is limiting. Then we have to find out the theoretical mass of hydrazine, then apply the percent yield to get the actual amount. All right? So if we have N2 plus 2H2 yields hydrazine, N2H4, and we're given 25.57 grams of nitrogen and 4.45 grams of hydrogen. So we need moles of each one. Okay, nitrogen is 14.01 per nitrogen times 2 is 2802. Hydrogen is 2.02. So we need a calculator. 25.57 and 28.02 is 0.913. 0.913 moles of nitrogen. And 4.45 and 2.02 is 2.20 moles of hydrogen. Okay. These are 1-to-1. So this is also equals hydrazine. This would be 1/2. 2 of these for every one of those. So this would be 1.10 moles of hydrazine. Okay? Nitrogen is limiting. So we're going to have 0.912 moles of hydrazine. Now we need to convert it back into mass. So 2 nitrogens is 28.02, and 4 hydrogens is 404, which is 60232. Well, that gives us the theoretical amount. 29.2. 29.2 grams theoretical. And the percent yield is 82%. So if we multiply that times 0.82, we should get 23.9. Which is B. Close enough. 24, 23.9, pick the best answer. What's the molar mass of tetraphosphorus decaoxide? This one, this is a type 3 compound. You need to know what the prefixes mean. So, tetraphosphorus decaoxide. And you need to know the molar mass of that. So 4 times phosphorus, 10 times oxygen, add them together, and you should get 284. All right. Are we ever going to get to chapter 4? Which of the following samples contains the greatest number of moles of carbon atoms? All right. I'm going to set it up. I don't want to run out of time, so I'm going to set it up for the first one. 58 grams of C4H10. 58 grams of C4H10. We need to convert this to moles, and this is the moles of C4H10. Okay? So that would be 12.01 times 4, and then 10 times 1.01 add together is 5814. 58.14. That's about 1 mole of C4H10. But the question is, greatest number of moles of carbon atoms. This has 4 carbon atoms for every 1 molecule. So it would be 4 moles of carbon for A. Set them up exactly the same way as that. What you need is the number of carbon atoms per molecule to finish the steps. You need a different value here for each one, and then you need a different value here for each one. And you should come up with which of the following samples contains the greatest number of that's not even the right answers. 69 is a mess. Which of the following contains the greatest number? Oh, no. Excuse me. My mistake. 46 grams. That'll be different for B. 44 for C, 180 for D. Then you do the conversions, right? We don't have time to do all those, so I'm going to let you do those. An unknown molecule consists of 24.2% carbon by mass and 4 hydrogen, and the remaining is chlorine, right? You know how to do that. Just subtract these two from 100. What's the molecular formula if it's found to be approximately 150? Let me see. 1, 2, 3, 5, 6, 7, 8. Okay, I'm gonna have to skip. We're gonna run out of time if I do this one. You know how to do empirical formula, molecular formula. You just need to find out what the empirical weight is for your empirical formula, and then multiply it by 1, multiply it by 2, multiply it by 3, and find out which one comes close to 150 without going over. And then you'll have your answer for the multiplier. This one is a case where you have atomic masses are actually given for each of the isotopes and the percentages. You know how to do the weighted average for that one. I don't need to go into that one. Let's see. How about this one? Okay. For number 73, you might be surprised to learn how many students get this one wrong. The empirical formula is the simplest whole number ratio of atoms in a formula. So if you count up these actual representations of formulas, the first one is 6 carbons and 6 hydrogens. So the 73. A is going to be C6H6, but the empirical formula is the simplest whole number ratio, CH. B is fairly simple. That's 4 hydrogens and 2 carbons, so the ratio would be 1 to 2. And then this one you have to count up, and you find that the empirical ratio is 1 to 1. This, when you count it up, the empirical ratio is 350. So we have, it looks like 2 oxygens, we have 10 hydrogens, and 6 carbons, which means that you just take half of those, and that gives you your empirical formula. It's shocking how many students miss that one. They just don't remember their definitions, I think, and more than likely, they don't practice them. All right, now we're in chapter 4. All right. So an unknown substance dissolves readily in water, but not in benzene, which is a nonpolar solvent. Molecules of what type are present in the substance? All right. If it dissolves in water, water is polar. Benzene, which is C6H6, is nonpolar. This is polar. You just need your rule of thumb. Like dissolves like. If the substance dissolves in water, it must be polar. Right? That's why B is the answer. It has to be polar. Okay. Number 5. Which of the following is not a strong base? All right. Strong bases are composed of alkali metal hydroxides and alkaline earth hydroxides. That's A, B, D, and E. Ammonia is not any of those. Ammonia then is a weak base. Okay, about 6. Which of the following is paired correctly? Incorrectly. All right. A, sulfuric acid is a strong acid. B, nitric acid is a strong acid. That's wrong. There you found your answer. Barium hydroxide is a strong base, hydrochloric acid is a strong acid, and ammonia is a weak base. So we found our answer. The incorrectly paired is B. Excuse me. We didn't talk about this one in class. Number 7. B. Number 7, the man who discovered the essential nature of acids through solution conductivity studies is Arrhenius. That would have been in your textbook in chapter 4. We didn't discuss that in class, so that just drives home the point. You need to read your textbook. Number 9. .4 gram sample of HF is dissolved in water to give 2 times 10 to the second milliliters. That's 200 milliliters. The concentration of the solution is what? Well, all the concentrations are in molarity. Molarity equals moles divided by volume, and volume has to be in liters. Right? So how many moles do we have? It's not given. We have to calculate it. 16.4 grams. So what's the molar mass of HF? Well, it's 1.01 and 19 for fluorine. So that's 2001. That'll give you the number of moles. It's 0.820 moles. So 0.820, and then how many liters is 200 milliliters? 3 places to the left is 0.2 liters. So I did that wrong. Let's do that again. There we go. 4.1 molar. That's D. Let's see. What mass of calcium chloride is needed to prepare 3.950 liters of 1.49 molar solution? Right. In this case, we're using the same formula. And that's 14. But we're solving it for a different variable. What mass of calcium chloride? Well, there's no mass in that formula. But if we find the number of moles, no problem, because we have the formula for calcium chloride. So we're actually solving it for moles. Moles equals molarity times volume. So the molarity is 1.49 molar and 3.95 liters. Okay, that'll give us the number of moles. Which is 5.89. Now we can convert moles to mass. So what's the molar mass of calcium chloride? Well, calcium, I think, is 40. 40.08. And chloride, we have two of them. 2 times 35.45. Okay. 40.08 and 35.45 times 2, add that is 110.98. 110.98 times 5.89 is 65.3. Which is, oh, excuse me, wrong decimal place. One more move. See, that didn't make any sense. 6 times 100 is 600. So I should have seen that one coming. So that's E. (16) What mass of solute is contained in 256 milliliters of 0.838 molar ammonium chloride? All right. I shouldn't have to work this one out completely. What mass of solute? The mass we can't get from the formula. We have to get moles first. So if we use this formula and we solve for moles, then I'll set it up for you. 0.838 and volume has to be in liters when the formula is in this format. 0.256 liters. That will give you moles. Then you need molar mass of ammonium chloride, right? In which case you need to know how to write ammonium chloride to get the molar mass. I think that's the real test of number 16. You have to be able to write ammonium chloride, otherwise you're stuck. You can't find the, you should come up with 11.5 grams. (17) 74.28 gram sample of barium hydroxide is dissolved in enough water to make 2.450 liters of solution. How many milliliters of this solution must be diluted with water in order to make 1 liter of 0.1 molar barium hydroxide. All right, this is, we have to calculate the concentration of the barium hydroxide to begin with. That's the concentrated version, and then we're going to dilute it. So it's a multi-step problem, and I will work this one out for you. 74.28 gram sample of barium hydroxide. 74.28 grams. We want to convert to moles. So we need barium hydroxide. Barium is a monster atom. 137.33. And hydroxide, we got 2 oxygens, 32, and 2 hydrogens, 2.02. So that's 5, 3, 4, 11, 6, 7, 171.35. Divided into 74.28. Is, yeah, 0.433. 0.433 moles. Okay, so now we can calculate the concentration of barium hydroxide, the concentrated version, the concentrated molarity, which is that many grams in 2.450. So this is going to be 0.433 moles per 2.450 liters. Which is 0.177 molar. Okay? So remember, molarity of the concentrated, volume concentrated equals molarity of the dilute times the volume of the dilute. So the question is, how many milliliters of the solution must be diluted? How many milliliters of the concentrated solution must be diluted? So we're solving for this one. So we want 0.1 molar and 1 liter from 0.177. And this volume is going to be in liters. So then we'd have to convert it to milliliters to find the answer. So 0.1 and 0.177 divide, and then 1,000 times 565. Yeah, 565 milliliters. Okay, that's A. All right, number 18. Let's see, what volume of 18 molar sulfuric acid must be used to prepare 2.3 liters of 0.145 molar? This is a dilution problem. So you need, the best way to do this one is to say molarity of the concentrated, volume of the concentrated, molarity of the dilute, volume of the dilute. What volume of the concentrated? That's the unknown. This one's 18 molar. We want to end up with 0.145 molar, and a total volume of, let's see, the answer's in milliliters. Let's make the volume milliliters. So what's 2.3 liters? 3 places to the right is 2,300 milliliters. Then you set up your problem, just like we did before, solve for that one. And you should end up with 19 milliliters of concentrated sulfuric acid diluted to 2.3 liters. All right. So now we're going to classify reactions. 28. So, for these two reactions, what do we have? What are our options? Oxidation reduction, redox. B is acid base, and C is precipitation. Okay. So what do we got up there? Do we have precipitation reactions? Yeah, we got two solutions on the left and precipitation on the right. Two solutions on the left, for both of them. We have precipitates. So this one is definitely an answer. Do we have oxidation reduction? Well, in order to be absolutely certain about that one, we'd have to do the oxidation states for each of the elements. So you need to know your rules. For the zinc bromide, for instance, we have to assume that bromine is -1. It's a halogen. Otherwise, we can't do the other one. This one's +2. Well, did the zinc change? Well, zinc nitrate, right? This one's a -1. This one's a +2. Zinc didn't change. And we look at silver nitrate. Silver is +1 and +1 on both sides. It didn't change. So the first one is not an oxidation reduction reaction. And that's the only one we need to do because we know that the first one's not redox. That means that they both can't be redox. So A is not a valid description because we know that one of them is not. Acid base. Neither one of those reactions has an acid in it or a base in it. So we know that the only one that works is C, precipitation reactions. How about the next one? All of the following reactions can be classified as. So if we find one that's not, then we can't say all of them. So all of them, rule of thumb, 29. We have redox, combustion, precipitation. A is redox, B is precipitation, and C is combustion. Right? Oh, I got them backwards. Sorry. Combustion and precipitation. Okay. Let's look at them. What's the rule of thumb for redox? If you can find it, element on one side is in a compound on the other side. Is that true for each one? The first one, yes. Aluminum is in a compound on the right, its element on the left. Silver for the second one is on the right, and silver in compound is on the left. That's a redox. Combustion reactions are always redox. Plus, oxygen is an element on the left, and it's in a compound on the right. So all of them are redox. Now, how about combustion? You have to have oxygen, elemental oxygen, in order to have combustion. It has to be a reactant. So we've only got one of them in there. So that means B doesn't work. How about precipitation? Well, in order to have precipitation, you need two solutions put together to give you, and it's a double replacement, to give you a precipitate. And none of them have that. Right? Even though they form a solid, they don't meet the criteria for a combination of solutions to make a precipitation. Right? So the only one that works is A. They're all oxidation reductions. Which of the following salts is insoluble in water? That's 32. you need your chart in useful information and look up combinations of cations and anions and see which one precipitates. As it turns out, all of them are soluble in water. Each one of those. Just look them up. You'll find that all the squares are clear. And of course, if you know the rules, you know that all alkali metals are soluble, make soluble salts. All nitrates are soluble, and most chlorides are soluble, with a handful of exceptions. So calcium chloride is soluble. So your answer there is E. All of them are soluble. How about 37? Consider an aqueous solution of calcium nitrate added to a solution of sodium phosphate. What's the formula of the solid formed in the reaction? Okay, calcium nitrate, right? Calcium nitrate. That's a -1. This is a 2+, so we need 2 of these. And that solution is added to sodium phosphate. Sodium phosphate. That's a polyatomic ion with a 3-, and this is a +1, so we need 3 there. Okay? Now, if these are aqueous solutions, that means we have calcium plus 2 nitrates plus 3 sodiums plus 1 phosphate. Okay? So now this combined with that is what? It's soluble. Sodium nitrate soluble. Calcium phosphate, we look it up on our chart, calcium phosphate is insoluble. So that means we're going to combine calcium with phosphate, which means we need 3 here and 2 there. Cross multiply. So Ca3PO4 taken 2 times is C. That is your answer. That's the precipitate. All right. For this one, let's see, 38 through 40. Do I have time to do that one? 45, 50, 52. Okay, I'm going to have to be quick with this one. Here we go. 38, 39, and 40 are based upon the reaction of barium chloride and silver nitrate. The balanced molecular equation contains which of the following? All right, let's do that one because you need to know how to write each one of these equations. And 38, 39, and 40. First of all, you have to write the compounds. Barium chloride. That's a 2. Is combined with silver nitrate. Silver combines with chlorine. To make a solid. And barium nitrate is soluble. And this needs to be 2. Okay. Now let's balance it. 1 barium, 2 chlorines, 2 silvers, 2 nitrates. That's balanced. Once you've got the equation balanced, then you can answer 38. Which one of these is contained in that reaction? And take the coefficients into account and the phases. Silver chloride solid, 2. So that's B for 38. The others don't match up. 39 requires you to write the complete ionic equation. So barium, 2+, plus 2 chlorines, plus 2 silvers, plus 2 nitrates yields 2 silver chlorides plus a barium plus 2 nitrates. Okay, once you got the balanced molecular equation, you just split out your ions and take the coefficients, take the subscripts into the coefficients. So 2 here means 2 there. All right, so which one of these is correct? 2 silvers right here. So that's C. For the net ionic equation, we just cancel the spectators. So we got silver and chlorine make the solid, so we have to keep them. But barium is on both sides, and nitrate is on both sides. So now we have this one, this one, this one. But notice they can be reduced further. 2, 2, and 2 means 1, 1, and 1. So if we do that, that, and that, now we have 1 silver, 1 chloride yields 1 silver chloride. So which one of these is in there? 1 silver. That one. So that would be A. That's how you answer this question. And you have to know lots of things. You have to know how to write the compounds. You have to know how to put them in the chemical equation. You have to know how to balance the equation. Then you have to know how to split them out into their ions. All right. '45. When solutions of strontium chloride and sodium sulfate react, which of the following is a spectator ion? Well, all you have to do is say strontium chloride, which is 2, and that is added to sodium sulfate, like that, aqueous. You do a double replacement. You say sodium and chloride. What does that make? That makes a soluble compound. Those are spectators. Strontium sulfate is a solid. So the strontium and the sulfate have to be kept. Sodium and chloride are spectators. So, which we have sodium ion and chloride ion. 2 of these, chloride and sodium, those are both spectators. Let's see, I'm coming up on 3:45, is it? Oh, I got till 3:50. Okay. I had 12 minutes. What mass of sodium hydroxide is required to react exactly with 25 milliliters of 2.7 molar sulfuric acid? All right. This is an acid-base reaction. And probably the most efficient way to work this one is to write the acid-base equation, which is sodium hydroxide plus sulfuric acid, makes what? It makes the salt, sodium sulfate, and water. So how do we balance that? We need 2 sodiums and we need 2 waters. So this tells us the ratio of sodium hydroxide to sulfuric acid. If we know 25 milliliters of 2.7 molar sulfuric acid. Remember, moles equals molarity times volume. So if we say 25 milliliters times 2.7 molar, then what are we going to get? We're not going to get moles, we're going to get millimoles. .5 millimoles. Okay. What's the mass of sodium hydroxide that will react with that? Well, the ratio is for every one of these, you need 2 of those. So times 2 equals the millimoles of sodium hydroxide. 135. Okay. Now here's where we have to go back to moles, because in order to get mass out of this, we need moles. So 135 millimoles is 135 times 10 to the minus 3 moles of sodium hydroxide. So now we need moles, molar mass of sodium hydroxide. All right, so sodium is 23, 23. Oxygen is 16, and hydrogen is 1.01, which is 40.01. Times, let's see, let's do that, and divide by 1,000, and then multiply. 5.4 grams. C is your answer. Now, if these problems seem difficult, all I can say is you haven't worked enough of them. If you're not working these problems in the review document, then you're going to be lost. .52, in which of the following does nitrogen have an oxidation state of +4? All right. Let's see. I think we got time to do this. A, B, C, D, and E. Yep. Sodium nitrite, ammonium chloride, dinitrogen monoxide, which is laughing gas, nitrogen dioxide, and NO3. We're looking for +4 oxidation state for nitrogen. Right? If this is -2 and this is a +1, then that's a -6. -6 and a +1 equals a -5. So this has to be a +5. That's not it. -2 is a -4 + 4. There it is right there. It's B. Now you can do the rest of them, if you have time, if you want to, but we found our answer. All right, 53. The oxidation state of iodine in IO3-. What's missing? The cation. IO3- is an anion, and we don't like unbalanced charges. But we left the cation out because it won't matter. Because the IO3- tells us that the summation of oxidation states must be equal to -1. So if we've got -2 for oxygen times 3 is -6, and we need one of them to be minus, we only have to balance a -5. So that's +5. Check yourself. -6 and a +5 is a -1. So D is your answer. '55. Which of the following statements is not true? All right. A through E. Let's see. A, when a metal reacts with a nonmetal, an ionic compound is formed. True. B, a metal-nonmetal reaction can always be assumed to be an oxidation-reduction reaction. Yes, because you have elements on the reactant side and a compound on the product side. C, two nonmetals can undergo an oxidation-reduction reaction. Oh yeah. All they have to do is change their oxidation states. And we've calculated some of those. That's true. D, when two nonmetals react, the compound formed is ionic. Nope. Two nonmetals react, it's always covalent. They have to share electrons. And E, a metal-nonmetal reaction involves electron transfer. That's true. That's a redox reaction. So D is the only one that's wrong. Let's see. Coming down to the wire. In this reaction, calcium plus oxygen yields calcium oxide. Which species is oxidized? All right. Two calciums plus an oxygen yields two calcium oxide. Okay, gas, solid. Okay. These are both 0 because they're elements. This one's a -2, this one's a +2. So, which one's oxidized? Oxidation is loss. Which one lost electrons? Well, if we go from a 0 to a 2+, that means it had to lose 2 electrons. So that's it. That's the oxidation. Calcium, the calcium metal, C, is the one that was oxidized. Let's see. Oh, we got a different one here. 57. In this reaction, chlorine is what? Okay. Cesium plus chlorine yields cesium chloride. Okay. So let's identify what happens here. This one is -1, this is +1. Is that right? Yeah. Cesium is an alkali metal. It's always +1. Okay, so if we go from here to here, that's a loss of 1 electron per cesium. This is oxidation. That means this one must be a gain of 1 electron per chlorine, which is a reduction. Okay, that means if this is oxidized, this must be the reducing agent. And this must be the oxidizing agent. Okay, so the reducing, let's see, chlorine. Chlorine is the oxidizing agent, B. All right, but it can't be the oxidizing and reducing. Chlorine, is it oxidized? No, it's reduced. Is it the electron donor? No, because it gains electrons, right? So the only answer in that set is B. It's an oxidizing agent, and that's the only possible answer that's given. All right. Which of the following statements are true? Oxidation and reduction. Let's see. A, cannot occur independently of each other. That's true. They have to occur together. B, accompany all chemical reactions. No, not always. C, describe the loss and gain of electrons respectively. Oxidation is loss, reduction is gain. True. A and C are true. How about D? Result in a change in the oxidation states of the species? Yes. A, C, and D are all true. B is false. 63. We might run over a minute or two. Balance the following oxidation reduction reaction using the oxidation number method. In the balanced equation, the coefficient of Br minus. Okay, this should be fairly quick. Fe plus Br2 yields Fe3 plus Br minus. Okay, 0, 0, 3 plus, and minus 1. So this one is a loss of 3 electrons per iron. This one is a gain of 1 electron per bromine. Okay, so we need 3 electrons down here. But how do you put a coefficient in there to give you 3? If I put a 2 here, that's 4, right? Because if I put a 2 there, that's only 2 electrons. So what we have to do is actually cross multiply. In other words, we've got to settle on a value of 6 electrons. Okay, which means this is times 2, 2, and 2, and this is times, well, we need 6. So we need 6 here, and we need 3 there, times 6. Okay, so 2, let's see if it, 2 iron, 6 bromine, 6 bromine. That's correct. Yep, and it gives us the right balance of electrons, too. So the oxidation number, coefficient of Br minus is 6, right there. We got more. Okay, hopefully this won't take too long because I'm out of time. 66. Okay, select the spectator ions for the following reaction. All right, the spectator ions, the best way to do that is to identify the solid. Lead 2 chloride is a solid. You can look that up in your table. That means potassium and nitrates are all soluble. So potassium +1 and nitrate -1 are spectators. There they are right there. 68. Identify the precipitate formed, if any, in the following reaction. So you just trade cations. So iron and carbonate. Is that a precipitate? Well, it depends. What's Fe nitrate? It's 2, Fe2. Fe2 plus. And carbonate is 2 minus. So FeCO3 is a solid. Right? So B would be a correct answer. Ammonia and nitrate is soluble. Right? So that doesn't work. We just had to get the formula for iron and carbonate correctly written. Following, does nitrogen have the highest oxidation state? In which one? All right, you have to go through and determine the oxidation numbers and compare them. Should come out with nitric acid. 71, in which of the following does iodine have the lowest oxidation state? Well, same thing. You have to determine what is the oxidation state of iodine in each one of these. and compare them. And you should come out with D. That would be I minus 1. That's the lowest oxidation state. In other words, the more negative it is, the lower it is. So if you've got some positives in there, then you'll have some high positives, mid, low positives. Once you get into the negatives, I2 is 0, but I minus 1 for D is the lowest oxidation state. And hopefully that's all the ones I had planned. Yes. Okay, that's it. Let's go down. Be sure. Yep, they're there. They're there. Okay, all those are there. And you're okay. So everything's here in the review document. It will be there on the exam. Okay, that's it.